Hello, I'm Steve Miller. The title of my talk today is Reversing the Reversing of the TriStation protocol. It's mostly a story about me learning about industrial control systems, ICS, security, which I had a couple months ago know nothing about, and three T's in particular, Triton, TriConnex, and TriStation. I'll explain what all of those are shortly. A little bit about me. Steve Miller. I am a researcher at FireEye/Mandiant. I used to do host-based forensics. Now I do network stuff and dabbling in ICS stuff. I live in the US, in central New York. New York's a big state. I live in a little tiny town right in the middle. I've been playing the Battlefield 5 open beta. I don't know if anybody plays that. But my grandma thinks I play video games for a living, so it's suitable. And that's a picture of my motorcycle, BMW F800 GS, when I was riding through Northern California about a year ago. I am on FireEye's advanced practices team. We have a cool logo. It's an eagle shooting two desert eagles. So we think we have a pretty cool logo. Anyway, that's a little bit about me. This is just to get you into why I became interested in security. It wasn't this, but when I was traveling, I was living in Australia, and my mom received a letter of mail from the US Office of Personnel Management. And it was about a year after the OPM hack went public. They decided to send mail to everyone, which was nice of them. But the US OPM manages the records of all the government employees. So my entire security clearance and everything the government ever knew about me is now owned by China. You could probably look it up on the dark web if you're interested. But anyway, that's kind of why I'm into security. And for the next about 28 minutes, I'll talk to you about Triton, which is a malware framework, TriConnex, which is an ICS PLC, Programmable Logic Controller, and TriStation, which until recently was a undocumented proprietary network protocol. So this is really just my interest in these subjects, and I kind of poked at them for a little bit. And I hope you will learn something. I'm not sure what. You all have different backgrounds and different interests. I'm not sure what you'll take away from this, but we will see. So, Triton. Sometime around December 2017, I think FireEye released a blog about the Triton malware framework. It was written in Python. It was found at a customer site in the Middle East. It was compiled in py.exe, and it was designed to interact with TriConnex controllers. This is the first of its kind. We live in an industry where everything's like a total game changer, but I think this is kind of a game changer. So it's designed to interact with TriConnex controllers. This is what a TriConnex controller looks like. There's like three of everything. Triple redundancy controller, TriCon, very clever. But it's a PLC, and this is a particular type of PLC which is designed for safety systems. So it connects to sensors, and if the sensors see something, they have logic that turns a gizmo or a motor or a widget and controls some industrial process for safety reasons, so that things like oil refineries don't explode, which is, I think we can all see some value in that. So petrochemicals, oil and gas, power, pharmaceuticals, anybody with a industrial plant that wants to have safety systems. In a plant, you might have hundreds of these, literally hundreds, and they could be all over the place, and they are networked, of course. TriStation is, for the purpose of this talk, will be the protocol, the binary protocol that allows a PC running some software to communicate with the TriCon or TriConnex controller. So everybody got their TriCon, TriConnex, Triton. TriStation. We got a lot of buzzwords here, so I will try not to mix them up. Sometime earlier this year, it was like probably May, somebody was like, you should look at the Triton malware. I was like, wow, that's cool. I didn't have anything to do with it when my company responded in the incident response. And somebody was like, it uses a proprietary protocol. And I was like, what does proprietary mean? I don't know. And there's like, it's undocumented, and I'm awesome. Undocumented things are my favorite things. So I thought to myself, I became really like curious, how does this malware framework use the protocol? What does the protocol look like? I asked around, nobody had any PCAP, which is my worst case scenario. There's no PCAP. So the big questions for me, and this was part of my job, right, was to, what the hell? What the hell's going on? How does the TriStation protocol work? What does it look like? To what extent did the malware authors reverse engineer the protocol? How did they do that? And how did they build a malware family that spoke with this protocol? And then to what extent did they implement the protocol network stack into the malware? These are important questions because if what I've observed in looking at a lot of malware is that when you implement a protocol, you have a very good chance of doing it wrong. And if they did it wrong, if there was any sort of error in their implementation, then we would be able to detect that, right? That was a kind of guess, and that is true for a lot of other protocols. I was kind of hoping it was true for this one. So I wanted to poke at that. This is kind of what it looked like in practice. I stole this from the FireEye blog. But you have a PC over there, and that's running some sort of special software. The trilog.exe is the Pi-to-exe compiled malware. And inside of that, it has a bunch of scripts, and it talks to the controller. And the purpose of the malware was to communicate with the controller, the Tricon controller. So I had to talk to it, had to reprogram it or manipulate it, and ultimately exploit it. And the purpose of this was to inject a custom binary backdoor. The controller does not run Windows. It does not run Linux. It has its own custom architecture and firmware. I'm not qualified to talk about any of that, so I decided to kind of focus on the networking protocol. So trilog.exe, to break it down a little bit, anything that's written in Python and compiled with Pi-to-exe can actually be uncompiled. And when you compile, you have the option of specifying some zip files, but developers and malware authors being lazy, like me, used all the defaults. So all the scripts were just compiled there, and inside of the main executable stored inside a zip file called library.zip. And this is what, when we uncompile it, it kind of breaks out. PYC is a Python bytecode, but that's actually pretty easy to uncompile as well. And after all of this, we're actually able to break down the plain text scripts. So unpi.exe and uncompile6, these are on GitHub. You can go download them and do this yourself. So this is kind of what the logic looked like. So back in this one, I looked at all these. So it's like 240 Python scripts in here. Most of them are just default Python stuff, support different types of functions. But there were a bunch of them that obviously seemed very specific to the malware and specific to the implementation of TriStation. So these are the ones, evil stuff.py, that's the main routine of the malware. That was what was going to inject the controller with the backdoor. And then we had all these other things, but you could see it's a very nice cascading logic. Evil stuff imports TS high imports TS base, and so forth. And so all the way down that chain was where I decided to start looking at the plaintext content of these scripts. So I'm looking for the implementation of TriStation. When you look and you want to document an undocumented protocol, there are a couple things you got to look for. You want to look for magic values. You want to look for counters. You want to look for timestamps, padding. There are a lot of different things, but when you want to document a protocol, you want to look for the structures, the major structures. And there's a lot of other things, but those are kind of the basics that you go into. And this all turned out to be much easier than I thought. So when I opened up cnames, tscnames.py, what was apparent was that it was just basically a bunch of arrays with string text, and these string texts were attached to kind of integer values, and you get the sense that it serves as a library for something else. But then when I want to go look at where these arrays are referenced in some of the other scripts, we kind of have to dive into some of the functions. So we can see that this is an array called tscst, and that tscst is referenced as it's a dictionary result, so used as a library of strings for TCM result. And so that was the function I wanted to go look at next. So we look at that, and that's actually in a different Python file. And right here, we're already seeing that they're breaking down the TriStation protocol in some way. When we have a bunch of UDP data coming back, we see that the first 4 bytes are broken into type and size. So pretty straightforward. And then the last 2 bytes are a CRC. So it's right there. It's really easy. We didn't have to do any reverse engineering. We did it the easy way. So that's pretty cool. And if you want to document a protocol, you can do it in the kind of C structure. I call this the pretentious way. I just kind of penciled it down on a napkin. And then what I wanted to do is dive in a little bit further, and then going into TS result, we also saw that the next bytes after those first 4 bytes, this is packet type 5, and in that first array I showed you, type 5 was a command reply. So just for command reply packets, we now have these additional fields broken out in the data. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 more bytes are unpacked there. So now our understanding of the protocol has grown a little bit, and we can document that. And just based on the variables in the code, we could get the sense that this stands for something or the other. Size and checksum are unknown. Anybody label anything unknown? Probably not, maybe. But anyway, so this is the command type structure, and that's all well and good. Oh, what was that? Oh, and okay, the commands, and then so that particular byte was referencing a different array in that first Python file, and it has all these, all these different strings for what the command reply is. So that's really cool. We're seeing that the malware authors had a pretty good understanding of this protocol. They have all these message types, yada, 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 right? So I wanted to validate that the structure of TriStation that they knew was actually true. I wanted to see if they made any errors or anything. So obviously I Googled around. I asked a bunch of people for PCAP. Nobody had PCAP for me. It was a sad day. I found a paper by the Coordinated Science Laboratory at the University of Illinois Urbana-Champaign. That's a mouthful. This is a really cool paper. It was behind a paywall. I did Google long enough and found like one of those PDF reproduction sites where they try to sell it to you for $1, but you can take a screen cap of all the stuff. And I read the paper, and there were a couple of things that these researchers did. One, the TriStation protocol, which is undocumented, is similar to a documented protocol by the same protocol author called TSAA. And the researchers used one protocol to make inferences about how the other protocol worked. And they also were able, and they did that, and then they did some testing of their own, and they documented the TriStation basic structure. And so this is what it was like, which validated a lot of what I saw in the Triton framework. And what do you do with a protocol structure, like once you've got it? First thing that I want to do is dissect some PCAP, but I didn't have any PCAP. But they printed out some bytes in their paper. So I kind of noticed, I was like, okay, if that's a real TriStation packet from their experiments, And I also noticed that we were talking about command type 05, and I noticed that everything before the 05 was actually probably UDP header data. So I tried to OCR it, but when you take a screen cap of this, you get a lot of O's instead of zeros in an OCR. So I typed all of this into a hex editor very slowly. I know, it's terrible. I'm embarrassed that I had to do that, but I did. And I stripped off the UDP header bytes, and then I used some CyberChef to print it out to like a fancy text file, and then I used text to PCAP to generate my own PCAP. And then I went on a journey of opening it in Wireshark. There's no parser. No parser existed for this publicly, no dissector. I created a really terrible Lua dissector. That's up on my GitHub. It's awful. But you can go look at that and dissect that PCAP. And then about a month later, the Nozomi guys really showed me up. And they produced a totally badass dissector for this protocol. I recommend you go check it out. But that's one thing you could do once you understand the structure of a protocol. This is that same PCAP that I typed out, but dissected by the Nozomi TriStation dissector. As you can see, it breaks down the protocol into the channels, the data length. This is the result of a custom protocol. They put the data length twice. I don't know why. I probably wouldn't do that if I were designing one. Anyway, there are a lot of things about this protocol that are weird. But we also have to remember it was written probably like 20 years ago. What else can you do with the protocol structure? You can observe the traffic in real time if you know kind of what it looks like. I tend to favor Snort because all my sensors use Snort, and it's really easy language to kind of write in for packet matching. So if we knew that value 1 type, the first 2 bytes, if the type was 1, it'd be a connection request. And we also know that probably the smallest size packet is 6 bytes. We can kind of guess that type size and a CRC, and because we don't know CRC, we could pretty much calculate that, CRC 16, and then we could write a very simple Snort rule that does a content match for that, looking for UDP traffic. So what this would do if you push this out to a sensor, it would detect if there were a TriStation connection request on UDP on the default port. And Snort rules are really good for identifying traffic that you want to observe. BSI in Germany, they did some awesome research on the TriStation protocol. This guy, Thomas Schmidt, led the charge in creating a Snort rule set for intrusion detection systems. It's free, it's accessible to everyone. And again, before a couple of months ago, nobody had any visibility into this traffic. So this is like a super awesome research project that actually delivered some value to anybody who owns Tricon controllers. This is what that Snort set looks like, and it depends on a bunch of configuration stuff. But it's out there, you can Google for it. It's pretty straightforward. So how was Triton developed? Now that we kind of looked at all that stuff, when we decompiled the Python bytecode, uncompile 6 kind of gives us a guess at the compile time. I'm not sure 100% how accurate this is. I assume it's accurate. But there are about 200 or so Python bytecode files in library.zip. And my boss, this is my boss now, he tweeted out this picture. I tried to make a graph, and I was like, you know what? He already did it. But this is what the timestamps on the Python bytecode inside library.zip kind of told us. And what's interesting is you can see that there are a bunch that were in June 2016, and that what we see were a couple of edits later in 2016, November, and then 2017 we started to see some more stuff, and August 2017 is when we started to see the last modified times of the TriStation implementation. So we know that this malware framework, they spent like a good solid year on it, maybe more. I would guess more. And we can tell that from the Python metadata. There were some discrepancies in the Triton malware code, and I became really fixated for no good reason on this. There were a couple of misspellings in that first library of arrays that made me very curious. And there were also a bunch of strings in there, and I was Googling for them everywhere, and I couldn't find any trace of any of this. Most of the Triton code is mad decent, yo. It's pretty solid, has nice cascading logic, there's good annotations, everything, the variables seem well named. So like, to look at that library of weird misspellings, and then the rest of the code seemed to be pretty solid, it was really inconsistent. There's nothing that drives me more insane than inconsistencies. So like, here's an example of some of the arrays that I was talking about, allocate, label. Here's one that just drives me crazy, is just a case inconsistency. These are small things that I become very fixated on, and I'm wondering why these arrays are so different from the rest of the code. Response, there were probably a bunch of these, and I don't know, there were probably maybe 10 or 12 misspellings. So I'm like Googling around for these, and I couldn't find anything. So obviously, I have access to VirusTotal Intelligence. Does anybody use VirusTotal Intelligence? A couple people. There's a reason that I go to VirusTotal Intelligence, and we heard from the Virus Bay guys earlier, is that a lot of people, a lot of products will submit files willy-nilly to different types of things. And I basically look at this as a file repository for both good and bad. It stores everything. I'm expecting that a bunch of people submitted some stuff, and I want to try to look in there and see if there's anything that relates to the Triton malware inside of VirusTotal. So I go on a retro hunt, and a retro hunt has its limitations because it only goes back on files submitted within the last 6 months. So I came up with a big fat 0, which is an extremely disappointing result for me because I wanted to find something. And to work around the limitations of VirusTotal, we have a tool called Awesome Possum. Awesome Possum is an internal tool. We take all VirusTotal submissions and we index all the metadata because we can search back forever, and we throw in a big log and Elasticsearch and all that. But one of the interesting things in Awesome Possum is that I can search by submission names back forever all the time. So anyway, I got a sense in documentation that I would be searching for ts1131.exe, and Awesome Possum, that is awesome, presented a bunch of results for me. We can track the submitters and see all that stuff. So that was pretty cool. So I went on this kind of hunt to look for source files. And first thing I do is try to run it in a VM, and I obviously see that I'm missing all these kind of dependencies. And I did this for a while. I just like kept looking in Awesome Possum to see files submitted with that name. I download them, and I try to reconstruct this package. Eventually, I went to Dependency Walker and got a huge list of DLLs that I thought were related to the legitimate TriStation software. So all along, we had this narrative that the Triton malware was built with understanding based on reversing legitimate TriConX software. And that was a narrative, and nobody had any proof of that, and I wanted to go find some proof. So anyway, a bunch of things that I didn't have, and I was able to finally get to a file called lag.evn DLL that had a parent file, data1.cab, that had a parent file, and now I'm into some like juicy data, right? Trilog v4.1, and if you remember, the original Triton malware file mimicked Trilog. It was named trilog.exe. Presumably, this is related to the Tricon controller type of software. So anyway, I open this up. I start poking around in data1.cab, and I look through all these DLLs, and there's obviously one. I'm interested in the communications. So this one really stood out to me. Anything com.dll, named very cleverly. But you could see it's a DLL that supports Tricon communications interface. This is was written in Visual C++, and started dumping string tables, and I'm starting to see things that are pretty familiar to me. You know, all of these, like, okay, that looks like kind of like a thing. And then here we go, is like, we can see the inconsistencies, all these same strings. And if you looked, I probably spent 100 hours looking at the TriStation, or the Triton strings. And the moment I was able to look at this, I was like, okay, 100% know that all of these strings in this string table came from a legitimate TriConnex DLL. So I was like pretty happy with this result. And everything is in there. And it just goes backwards. Start, download, change, all of that. All the typos are in there. And so then I went and collected a bunch of DLLs. And I could see that, where was it? tricom.dll, they had these C++ string tables in there. All of these dated back like decades, right? So I'm looking at some library that was written ages ago, never updated, never, maybe not QA'd too well, I don't know. And I was trying to figure out exactly what software package was probably reverse engineered. I don't think I had any really good results from this, but there is an older version of a Tricon controller called a Trident, and these both have you know, different branches of software that were supporting the communications for these controllers. In any case, there's a couple of things that are still interesting about this, is that this is from the Triton malware code. There were some annotations in the Triton Python scripts that were above what they had reverse engineered from the Tricon libraries. And you can see that like these unknown values and this string here in particular are pretty different from, you know, the angle brackets kind of characterization for maybe unused integers in particular places. So it became apparent to me that the Triton malware developers, although they reverse engineered some of the legitimate software, they still had to do a lot of experimentation to figure out the network protocol. And we know that because not only did their malware framework take so long to develop, they had a really hard time using it in the wild, and they ultimately got caught before they were able to do too much damage. So, you know, again, 6 months ago or a year ago, we only had like the suspicion that they reverse engineered something. We're able to finally provide some kind of conclusive evidence to support that. So that was kind of a win for me. And then a year ago, the world had no visibility into the TriStation protocol. It was a black box protocol, undocumented. We have some documentation of it. The Nozomi guys probably know more than anybody about this protocol. We know that they had a hard time using it in the wild because when we went to the engineering workstations that was launching the Triton malware, we could see from the user journal, which is also, or USN journal, also called the change journal, I think universal sequence number. This is an NTFS feature that logs file names and change time. But we could see they uploaded like 100 different versions of the Triton malware. And they also uploaded like 100 different other scripts and 100 different other utilities. They had a hard-ass time getting there and then making this work. And I think the experimentation that they were doing ultimately led to the outcome, which is they caused one of the Tricon controllers to enter a fail state. That fail state, which is monitored by the industrial control systems monitoring software, induced a shutdown of this entire industrial process. And as you can imagine, if you run a big industrial plant, you're like losing $1 million a minute every time your industrial processes go down. So that's what got them caught. And last but not least, it's really important to acknowledge all of the public research that was done on this. I think I read everything for the most part. There's a couple of good FireEye blogs on this. The Nozomi Networks guys did a lot of research. They purchased a controller on eBay. and reverse engineered some of the TriStation software as well. I think doing maybe exactly what the Triton malware developers did. Dragos guys have a lot of good stuff. Accenture has an awesome white paper on this. The guy behind Midnight Blue Labs, ICS cert, CSL at University of Illinois. There's a GitHub repo with all of the malware and all of the decompiled scripts and then all of the resources. And all of this is important because ICS, if you think everything is broken IT, you gotta check out ICS. It's a different world. Everything's like 20 years old. And so a lot of that's just hanging out there. And if you're interested in ICS, there's no better time than right now to get into ICS security. And with that, I will take any questions. I think we got like a minute left. So.
Yeah, thank you. Like you said, you have 1 minute left, so there's at least one question, right?
Don't ask me who it was, because I can't say.